So today we're going to talk more about statics and torque and maybe get to a little simple machines. On Monday we will review for the exam, and Tuesday during lab time we will have an exam, and then there's no school on Friday, and yeah, the midterms are going to be due. Question? It's chapters 4 through 8. Okay, so I still have the same picture here, but it's not funny anymore. Picture of the Leaning Tower of Pisa. If you look here, there's interesting information about the Leaning Tower of Pisa. In 1350, it leaned only. Oh, great. We've also been working with the pin. We're changing batteries again, and it seems that probably is the most likely thing because I went back to the original battery and it worked better than it was with the replacement battery, so we're getting a new battery. I know, I'm nothing but technology problems. Okay, so when it was first measured in 1350 to have a significant lean, it was only leaning by 1.4 meters. That is, the top was 1.4 meters offset from the base. But in 1870, just a mere, 400 and some odd years, obviously a long time, it had gone up to 3.8 meters. In 1993, the rate of lean had increased, so it was up to 5.4 meters. And now you might notice in the title of this, it lost 2.5 centimeters of tilt. Now, given the tilt was 5.4 meters, losing 2.5 centimeters of tilt is not a major change. But that was due to them trying to buttress underneath and build it up so it won't fall anymore. Now, some of you are engineering students, and a civil engineer deals with problems like this. The building's leaning over, what's happening? Well, let's start with some basic things. And this is really basic, not to be insulting, but what holds up the building? The earth. We have a normal force from the earth pushing up to hold it up. And so if the building has a total weight of, that's pressure, a total weight of 142 mn. What does mn mean? Mega Newton. Because it's a capital M, it's mega. A lowercase m would have been milli, and that would have been ridiculous. So 142 million newtons, meganewtons, is the weight of the building. So the ground has to support all of that weight. The total upward force is 142 meganewtons. But when it tilts, it's leaning over. You can answer this without doing any physics. If I'm up here and I tilt over, I can get to the point where all my weight is on one foot. If I tilt a little less, I'll have a little weight on one foot and a lot of weight on the other. So when that tower is leaning, where do you have the bigger force? On the left side or the right side, as you view it? It's going to be bigger on the right. Yeah, that's, you said 2 trays, right? Yeah. It's going to be bigger on the right because it's leaning that way. Now, the total of the forces across, and this kind of looks like 2 feet. Each foot is going to have a different force. The one on the right, more force. The one on the left, less force. So they add up to that 142 meganewtons. But if you put more force on the one that's falling, what's it more likely to do? Has more force, so it's going to push down harder and be more likely to keep falling. So you can see the problem builds up, and they have to put something under here that's really strong so it won't keep falling. Now they calculate the torque, and you can see here the overturn moment. Okay, I've got to erase some other stuff so it doesn't interfere with this. The overturn moment. Who is an engineering student here? Just Cole. Okay, so Cole, have you taken a class where you've talked about moments in engineering?
Yeah, I'm taking statics.
Okay, taking statics right now. Moment is the engineering term for what we call in general physics or in any physics class, torque. So when it says that overturning moment, that is the torque that is trying to make it fall. And so the ground is going to have to supply a counter torque So the net torque is 0. If the net torque is 0, then the rate of rotation will stay constant at 0, and it won't fall over. And so there the units are MNM. What does MNM here? Notice it's capital M, capital N, lowercase m. What does that stand for? Meganewton meters. We can't use the term joule because that would be for energy. Even though a joule is a Newton times a meter, we use joules for energy, Newton meters for torque. So it's 327 meganewton meters that we need for the torque to counter that. And I'm not going to do any calculations on this, just that. A review on directions, because this is something that is very easily lost. Whenever you're working with torques, there is a direction to it, and you have to pay attention to that direction. Even if you have a, quote, one-dimensional torque problem, you can have a positive torque or negative torque. Positive means coming out, negative means going in. So for the torque, the method I taught you in class on Wednesday was using the right-hand rule. And that's your base rule. Now the right-hand rule works anytime you have a cross product. Cross product, R cross F is torque. Right up there in the top, torque is R cross F. If you have a cross product, your index finger goes in the direction of the first one, middle finger in the second, and thumb in the last. What would happen if you wrote torque as F cross R? If you put torque as F cross R, then what direction is your index finger point? F. And your middle finger points R. And your thumb would point in the opposite direction. So with torque, the order in the equation is important. It needs to be torque as R cross F, not F cross R. Now, that's one way to get the direction. Another way is a little simpler. If the torque is going to make it rotate, you can look at each one and just take your right hand and wrap your fingers in the direction that would make it rotate. So in the example right here, this arm is holding that physics textbook. You know these physics tomes are pretty heavy, right? Fortunately, you don't have one. Yours was free. So what would naturally happen to this arm if there were no muscles holding it stiff? It would naturally rotate like this. So you can take your right hand and say, okay, that rotation would rotate like this, and my thumb points in, so that's a negative torque. That is an equivalent way of assigning it. What you notice is that rotation was clockwise. So clockwise is negative. Counterclockwise is positive. Now on this note, if you are putting in a screw, a lot of people have memorized just a little four-word mnemonic to determine which way they need to turn that screw. What's that four-word mnemonic? Righty-tighty, lefty-loosey. That comes from the right-hand rule. Because the screws we use, we call them right-hand threads. Right-hand threads mean that they obey the right-hand rule. If you rotate it this way, it's going to go that way. If you rotate it this way, it's going to go that way. So our threads are called right-hand threads. You can get some screws that are left-hand threads. Left-hand threads, let's just compare. If you rotate it this way, right-hand thread will go that way, left-hand thread will go that way for the same direction of rotation. When would you see a left-hand thread? Well, you see them all the time if you work with gases of different varieties. Because you have some gases that are nice and safe, like helium and nitrogen. And so you make a regulator, and for inert gases, you just have this regulator you put on there, you screw it on, and everything's good. But what if instead of nitrogen and helium, you decide that you want to use, like I did in graduate school, something like krypton. Okay, krypton's an inert gas. That's not a problem, right? I was working with what we call an excimer laser, excited dimers that will laze. And so I worked with either xenon chloride or krypton fluoride. And everyone here, have you all taken chemistry at some level? Okay. No? Who said no? Okay, Eric. That's unusual. Everybody should be proud of Eric. Yeah, that too. Okay. Xenon and krypton are noble gases. They're not supposed to form molecules, right? They're just happy hanging out by themselves. But it's an excimer, it's an excited dimer. If you excite the energy levels for the electrons in krypton or xenon, you can make them bond with something. And so krypton fluoride is what I was working with. And fluorine gas is not a happy gas. It's very highly, highly reactive. You guys have all learned about electronegativity except for Eric. And so you know that fluorine is like just about the most electronegative you can get. And so, well, unless you go to some excited. Okay, so the fluorine is really bad. The fluorine will tear up your normal rubber gaskets in your regulators. And so they don't want you to use the regulator that you use for helium on a fluorine tank. Because what will happen is it will erode that rubber gasket, and then you'll have fluorine fill the room, and people will die. So what they do is they do things like they'll make regulators with different size threads, and they'll make some, like the caustic gases, so they're left-hand threads. So there's no way you can put the wrong regulator on the krypton bottle. Okay, that's a lot of work for, or a lot of discussion for something that was just, here's an example of how it's used. We are going to work some equilibrium problems. So here's an example of an equilibrium problem. I will work with something like this in a minute. Let's start with something very, very basic. Back when I was in high school, I worked at the dairy. And dairy and farm work together and harvest. Go out there, we chopped corn. We were growing green chop, and we chopped the corn. We then put it in a silo and let it ferment and get the cows loaded on fermented corn. So during the harvest season, of course, you're just constantly running the wagons. You get flats. When I was a freshman, little 13-year-old Richard was on the crew to change the flats. And it was really hard to break those bolts loose. They're basically rusted in place. And so I could take the regular old breaker bar and I could jump on it. I couldn't make it budge. But we had a cheater bar, which was just a pipe. And you put the pipe over the breaker bar, and then I just grab it and hang, and one of two things would happen. Either the wrench breaks, or it comes loose. Unless, of course, I got my righty-tighty, lefty-loosey wrong, then, What's the point of the cheater bar? Why did I use that, and why did it help me? Okay, it gave me a longer lever arm. The connection between where the pivot point is and where we apply the force we call the lever arm. So that cheater bar gave me a longer lever arm. And since torque, and remember, you must put the vector signs or it means a different thing. Since torque is R cross F, now my R vector goes all the way to there. Much bigger than my initial R vector, which would have been just that. And since the torque is proportional to R, I'm able to magnify my torque. In this case here, your torque is what? About 4 or 5 times greater than it would have been without the cheater bar. And since torque is the twisting equivalent to force, you got it rested in place, there's going to be a certain torque necessary to break it loose. I get that bigger torque, I can break it loose. So that's the whole purpose of the cheater bar, to increase your torque. Did it change the force I was applying? Not a bit. But I was able to break something loose that was stuck much more tightly by using what we call a simple machine. So a question just to make sure people listen to the last 1 minute of lecture. How does a cheater bar help remove a stuck nut? Ashley, Cole, Eric. Okay, Eric's answered.
I got signed out. That's fine.
Okay. Becky, Jeff. I said Leslie. So down to Ashley, Jeff.
What is this 30?
33.
It says that I'm through.
Okay. It does show 26 have answered. Oh yeah, it shows AP4899. Is that what it says in the back of your thing?
Yes.
Okay, so it has you separate. So Jeff. Nope. Okay. I just want to make sure everybody gets the credit right. I don't want to make it, haha, you lose. One person said increases the force you can apply. Nobody said increases the angle. 25 said increases the length. And nobody said it doesn't help. I'm glad nobody said it does not help, because it definitely helps. So Eric, give us some good reasoning.
It said it increases the length of the lever arm, and that increases the radius that you're turning it.
Which then allows you to have more which?
What?
Oh, this does. I thought that this said to increase torque. And so that's why I was asking.
No, it increases.
You are absolutely right, sir. It increases the length of the lever arm, and thus you get more torque. So you can get that stuck nut loose. Now, life will take a sudden turn toward the difficult. Here is a pretty standard problem. I don't think I assigned it to you. I hope not. You don't want to do your homework in class and then have you go home and say, well, no need to learn that. He did it. So here's a problem. Suppose an 880 kilogram car is on a bridge in the figure with its center of mass. The center of mass is a location where you can treat it as if all the mass resides. So for instance, if I were to take this meter stick, clearly the mass extends throughout the range of the meter stick. But the center of mass should be somewhere near the center. And if I push up at the center of mass, I can make it balance. So it's somewhere about there. Stop. Okay. So that's one way to find the center of mass, where the balance point is. Because if my upward force is the same location as the downward force, then there'll be nothing to make it rotate. So the center of mass is the location where you can treat it as if all of the mass is there. So for this bridge, we can treat the bridge as if the entire mass of the bridge is between the hinges and the cable attachment. And I don't know why it shows distances here, but it doesn't say as shown, does it? Yeah, it looks like, well, I'm going to have to use the distances here, I think, to actually answer it. So it shows that it's 1.5 meters from the pivot point to where the center of mass is. Now, what does it say here? It says CG. CG, oh goodness. I'm going to put a third battery in this before Monday starts. It's got to be the battery. CG stands for center of gravity. What would the center of gravity mean? Any ideas? That's where force of gravity appears to act. What would the difference in center of mass and center of gravity be? If we can treat it as if all the mass is at the center of mass, how would that be different from the center of gravity? The answer is a little tricky. For normal situations, there is no difference. But if you have an object that's large enough that the acceleration of gravity changes as you move from one part of the object to another, then they're going to be different. And the center of gravity is always the correct location to look for force, center mass, for some other things. But as long as you're treating G as a constant, they are exactly the same. So just treat them interchangeably. No, one's the center of mass. That's where the average position of the mass is. One is center of gravity. That's where the force can be treated as acting. So we have the center of gravity shown there. Gives us the mass of the bridge, the mass of the car. It says find the tension in newtons in the cable. How in the world can I find the tension in newtons in the cable given what we know? Does anyone have an idea? Possibly Cole because he's taken statics. Have you done problems like this yet?
Yeah.
And the nomenclature you learn there, of course, is going to be different than the nomenclature we learn here.
Yes, that's why
The process will be somewhat different, but the rules of what we're doing are the same.
So if I solve it, if I was to solve it the way I would normally solve it in statics, that's okay?
That is okay.
Okay.
If you're doing it correctly. As long as you show and know what you're doing, right? Not, well, I understand the answer 7. Yeah. As long as you show what you're doing. So what we need to do is apply our equilibrium conditions. How do I know I apply my equilibrium conditions? Because the acceleration of this thing is 0. And the angular acceleration is 0. Now keep in mind, it could be rotating at constant rate, and that's an angular acceleration of 0. But usually we're doing these as static problems, hence the name of the class Cole's taking, statics. In a static situation, the acceleration and the angular acceleration are both 0. So we're going to have some of the force vectors equal 0 and some of the torque vectors equal 0. So now we look at these and we have to decide what is our object that we're going to apply these to. Not always a simple question. So I will tell you for this one because it's the first problem we've done like this. The object I'm going to apply equilibrium to is going to be the bridge, that beam. And so once I identify my object, if I'm going to use some of the forces as 0, Newton's second law, I need to draw a Freebody diagram. And this Freebody diagram has to show the forces where they are acting. You don't just put a dot and have all the forces acting on that dot. You have to show it spread out. So here's my beam, and I have to identify each force on the beam. So I shall just start with people in the, I like to start in the back row. So trace, what is a force acting on the beam, and what is the direction? I didn't hear you. Okay, force normal. Now, in this case, an interesting thing to note, there are a couple interesting things. First of all, there's a big mass here that makes the center mass really close, but we're treating it as if there is no mass there, and the center mass is still here. We have the force of the pin that's shown with the capital F there. So we have that force of the pin, so I'm going to put F sub P. That force is not a technical normal force because we're not pressing against the surface, but it's the same idea. That's what's keeping that side of the bridge from falling. So you said normal force, I'm going to call it force of the pin, but it's the same basic idea. Its direction is not in the normal direction, so we couldn't call it the normal force because the pin, of course, is circular anyway. What direction is normal to the pin? So we have that force of the pin at some angle here that's unknown, so we marked it theta. Okay, next force, moving over Augusta. What's the next force? Gravitational force of what? There are two gravitational forces. That's why I said of what? Okay, of the bridge. And the force of the gravity of the bridge is shown here, 1.5 meters. So here I have force of gravity bridge. This distance here is 1.5 meters. Okay, Leslie, you are next on This Is Your Life.
Yay.
Another force.
The force. The bridge is being pulled up, right?
Well, it's a drawbridge and it has a rope there that holds the other end up. So there's not a normal force holding the other up. There's the drawbridge.
Oh wait. Oh okay. Maybe the force.
Don't know.
Okay, well, there's one shown there, so I'm going to go with that one for you. There's a force of tension shown in the picture. And so we have the force of tension, and it tells us that that's at an angle of 40 degrees. And then I'm going to skip over Eric because he already answered something recently. So Alex, what's the final force that's going to be acting on this system? It's the one that's not shown. The force, the other gravity. We're just looking at the forces right now. We're making our Freebody diagram. So Corso told you it's the other gravity. Gravity of what? It's not shown on the picture. The gravity of the car that's halfway across the bridge. So I have force of gravity car here. And so that's halfway across the bridge. If I add up 1.5 and 7.5, I get 9. So that's 1.4. That's very good. 9 divided by 2, 1.4. Everybody with me? 4.5 to get out to there. So now I've drawn a picture that shows all of the forces acting on my rigid object. And you look at it, and you're generally not pleased with things. How many forces do we have there? 4. We have 4 of them. Now, what's given to us? We are given the mass of the bridge, so that tells us what one of the forces is. We're given the mass of the car, that tells us what another force is. And we know gravity is vertical, so we know the directions of those two. We know the angle of the tension, but not its magnitude. So that's one unknown, the magnitude of the tension. And then we don't know the angle or the magnitude of the force on the pin. So that's 2 more unknowns. So we have a total of 3 unknowns. And so when you look at a problem, you have 3 unknowns. What's the standard thing that goes through your head? To solve this, I need 3 independent linear equations. But fortunately, statics problems make life a little bit easier because torque is R cross F. If I choose to sum my torques the right place, I can make R equals 0 to one or more forces. If I make R equals 0 to one or more forces, I eliminate them from my equation. And so there is one location where I have 2 unknowns. What's the one location where I have 2 unknowns? At the pivot point, at that pin. So I'm going to sum my torques about that point. And then I will have neither the magnitude nor the angle of that force matters. And I'll have one equation with one unknown. So when you're doing these equilibrium problems, that's one of the first things to do. Try to find a location where you can sum the torques to eliminate as many unknowns as possible. So I'm going to sum the torques about the pivot. So sum of the torques. Now, torque is a vector. In this case, all of our forces are going to be up or down. So they're all in the vertical plane. They might be at an angle, but they're in the plane between horizontal and vertical. And because of the right-hand rule, the direction of a torque is always perpendicular to the lever arm and perpendicular to the force. So the lever arms are in the vertical horizontal plane, and the forces are in the vertical horizontal plane, which means all of the torques have to be perpendicular to the vertical horizontal plane. They're all either coming out or going in. So I'm not going to write a vector sign. This is a one-dimensional torque problem. But I still have to keep in mind, is it a positive torque or a negative torque? Is it coming out or going in? So when I do these torques, I didn't put a vector sign, but I have to pay attention to the signs. So I'm going to show all of them, and I'm going to start, okay, so this is where I'm summing the torques right there. I'm going to just start with the force that's closest to the pin. So I will go to, coming up a row, Arlene. For this force of the pin, what do I have for my torque equation? Summing about the pin. Torque is R cross F, or R times F times sine of the angle between the two. Okay, this being the first time around the block, what is the radius from the pin to where the force on the pin acts, or force of the pin acts? No. No, it's not. Let's go back and just look at the words. The force by the pin, how far is that from where the pin is? What Jeff said. It's on it, so the radius is 0. So for the first one, I'm going to have the radius is 0 times the force of the pin, and we have to worry about the angle, so I would put sine of theta, but it doesn't matter because this term goes to 0 because the radius was 0. So now since Jeff helped her out, I won't go to Jeff. I will skip over and go to Edward. The next force in order is the force of gravity from the bridge. What's the radius for the force of gravity on the bridge from the pin? That's 1.5 meters. So I'm going to have 1.5 meters. The force of the bridge is going to be mass of the bridge times G. I know I could put in numbers for everything, but it's shorter to write MBG. Is that a positive or a negative torque? Since it's not 0, I have to determine it. So I want you to say if it's positive or negative and then explain how you got that. Now I know this is the first time around. You could be wrong, right? No one expects perfection when you're learning. But I want you to think about it. That's why I'm asking. Okay, negative and why? Okay, negative because it's going clockwise. Remember, that was one of the two things I gave you. If you would make it rotate clockwise, it's negative. Or using the right-hand rule for cross product, R is that direction, F is down, thumb goes in, that's the negative direction. So either one of those works, so it has a negative sign. So I have minus here. Now the next one, James. The next force is force of gravity in the car. So what's the radius for that? It's in the middle, yeah. Okay, so we have 4.5, and it's the force of gravity, so that's going to be mass of the car times G. And is that a positive or a negative torque? I didn't hear. Or maybe you didn't answer. It'd be a negative. For exactly the same reason that Edward gave us, it would make it go clockwise, rotate clockwise, or you can use the right-hand rule. So that's a negative. Now for the final one, and so I can't see who's next. So Brandon, our final force is the tension. What's the radius for the tension? Okay, so we have 9 meters. I got to at least put 2 sig figs here, 9.0 meters. And then what can you tell me about the force of tension? He can't see me. I've been mouthing for everyone nothing. You can tell us nothing about it except its direction. So that's got to be a variable t. And then we need one more thing because that wasn't perpendicular. So I need to calculate how much is perpendicular. So now I have to multiply by sine of which angle?
40.
40, because 40 degrees is the angle between the radius and the tension. Now somebody might be a purist and say, au contraire, it should be 180 degrees minus 40. It should be the complement to 40. Complement or supplement? Okay. You know what sine of 40 is exactly equal to sine of 180 degrees minus 40? So you can look at it either way. So we'll just put sine of 40 degrees there. And then finally, is that a positive or a negative torque? Positive. How'd you get that? Okay, so it's going up counterclockwise. I heard somebody say that would make it rotate counterclockwise, so positive. Use the right-hand rule, positive. So that's the sum of the torques. If it's in equilibrium, what's the sum of the torques going to equal? Now notice I summed about the pivot point. I could have summed about any location and the sum of the torques is still 0. It's just easiest to sum it about this location. So now I have this equation. How many unknowns are in this equation? Just one, just the tension. So the problem asks, what's the tension? I got there with one equation. There's still 2 unknowns, but I got there with just one equation. So now I'm going to just solve this. So these 2 are negative. Move them to the other side. The equal sign will make them positive. I'll have tension times sine of 40 degrees is equal to G times 1.5 meters times mass of the bridge plus 4.5 meters times mass of the car. Notice I factored out the G because both of those had a G. It's just going to be less work with the calculator. Finally, divide by sine of 40 degrees.
Where's your radius for the?
Oh,
The 9.
yes, the 9 as well. Yes, I forgot that. Thank you. If I haven't made it clear before, I very much appreciate being corrected. It's embarrassing to me, but it's far, far more embarrassing to go through and get to the end and say, what the heck happened? We all make mistakes. So now I can cancel, and I'm left with an equation. Okay, I'm going to check my numbers to make sure I did remember them. 882, yeah. So I see that we have at least one student diligently putting the numbers in the calculator.
7,047.
7,047?
7,037.
Okay, so we only have two significant digits, so it's 7,000 to correct significant digits, but I like to have larger numbers for intermediate answers. So there we found the tension. Now, like I said, life suddenly got a lot harder when we got to this slide, didn't it? So what were the steps I used in solving the problem? What was the first thing I did? I trust that you said this because I just heard showed, and showed was the word I was looking for the first one. I showed my rigid object that I was interested in and all of the forces acting on it at their location. So I indicated the position, the angles, the forces. That was the first step for an equilibrium problem. The second step, my conditions of equilibrium there. Apply those two conditions. Sum of the force is 0 and sum of the torques is 0. I chose the torques first because usually, not always, usually by using the sum of the torques equation, I can eliminate a number of variables and solve it with just that. Sometimes you need to use the torque equation one or two places, or there's different things you have to do. So it depends on the problem, but you apply those equations using your creativity. Now, we haven't solved everything in this problem. We've only solved part A. What's the tension in the cable? Part B asks us the magnitude of the force in newtons exerted by the hinges on the bridge. So what would I do to solve part B? It's just continuing solving it. Go ahead. Oh, I thought you were raising your hand.
No, sorry. Just go back to your sum of forces equals 0, and then calculate all of your different forces at their positions.
Okay. We now can just go back to sum of the forces equals 0. Notice it's a vector equation. Do sum of the forces in the vertical direction equals 0. That's going to give you force times sine of theta up, and tension times sine of 40 degrees up, and then the two mg's down. So that gives me an equation with two unknowns, the angle and the force. Then do the horizontal direction, which will be a simpler equation, the force times cosine theta minus tension times cosine of 40 degrees is equal to 0. That has the same two unknowns. Combine the two equations, and you'll be able to eliminate the tension and find the angle, or eliminate the angle and find tension. It's obviously easier to eliminate the angle or eliminate tension first and have tangent theta equals something. Then once you have theta, you come back and use the simple equation to find what the force is. So the method here is the same. All of your equilibrium problems are going to be this same method. But they're all going to be pretty complex. Well, almost all of them are pretty complex. And you have to do a lot of creative thinking on how to apply these rules. Cole.
Will we have to do any statics problems where we would have to, for instance, take the thickness of the bridge into account?
For us, no.
Okay, good.
For your other class, probably, right?
Yeah.
Because one of the funny things we have about engineers is we want them to design things that don't fall down and break. And so they have to be more realistic than we are in general physics class. Okay, what is a simple machine? Right? We talked about equilibrium and how that works. Simple machine, I've only got 4 minutes left. A simple machine is something that helps you do a job. It doesn't provide energy. So you have to put in all the energy to do the job. But what it allows you to do is use a smaller force over a larger distance of motion. So that's what simple machines do. They allow you to use a smaller force over a larger distance to do the work. So an example of a simple machine might be, okay, I will just break the meter stick if I use that, but I'll use it as a fulcrum. So I am going to take this mass, which is 1 kilogram, and, well, maybe I won't. It'll kind of work. Put it on there, And then this mass here is only 200 grams. Okay, 200 grams, I don't have enough length for that. I need to go to, this mass here is 500 grams. Is there any way that I can make 500 grams lift 1,000 grams? I can. Of course, why else would I do this, right? That was a rhetorical question. I once had a student complain, he asks rhetorical questions and expects us to answer. I can do it, otherwise I wouldn't have asked you. This is going to be a smaller force. But if I put it out here at the end, the torque this will provide, I have my fulcrum here at 25 centimeters. So the distance from here to here is 3 times the distance from here to here. So if I take 500 newtons times 3 25s, that's the torque that's going to be applied in, which, would this be a positive or negative torque if I put it on this side? Okay, it's going to be a positive torque because R cross F pointing out or counterclockwise. This one here is 1 times 25 times 1,000. That's a negative torque, but 1,000 times 1 is smaller than 3 times 500. So if I put it here, it should lift it up. Or make it tip over because that's the way of things. So this is called a lever. You might have heard the famous quote, give me a long enough lever and an appropriate fulcrum and I will move the earth. Right? Doesn't matter if this person only has the ability to put out a couple hundred, maybe 1,000 newtons. You have a lever that's infinitely longer on one lever side than the other. You can move anything. So that's where we have to end today. Have a great weekend. Have a happy Sabbath.